Assalamu alaikum wa rahmatullahi wa barakatuh. Today we introduce the classical cryptography. We will escape the parts that we introduced in the lecture. For example, we talk about the privacy and integrity of cryptography, talk about hash functions, introduced how to calculate hash functions. We said that there are two common hash functions in the market or commercially available, like MD5 and SHA, and we used that hash calc to define the confusion and diffusion. We defined the different types of cryptography, or cryptography and cryptanalysis. We said we have symmetric and asymmetric and protocols. We will talk about symmetric and asymmetric in detail. Block ciphers, symmetric has block cipher and stream ciphers. We talk about the difference between symmetric and asymmetric. We defined what is exactly is different in the lecture. And also we talk about Caesar cipher. We said that an example here, meet you in the park, can be changed to PHHW, something is not known. We explained all of these in detail. We also look at the side of the attacker. We said we can work like a hackers with for the Caesar cipher in three ways. We can use letter frequency analysis, brute force analysis, or tracing single spaced letters such as I, A, or double letters, words like N, F, and so on. And we have a letter frequency analysis because we have the letter E is repeated in English more than others. So we look at the ciphertext, which letter is repeated, then it should be the E, should be the E. Brute force analysis is trying every possible combination and specific letters. We talk about all of these in lectures. Even we have a lab to do that. We have this text and we try to decrypt it using the software here in this link. And we use the brute force analysis, and that letter, we found that letter not I, it is A, it is A, okay? And we have finished that exercise together. We tried to break the code. We look at the code, we found that this word is TOO and this is TO. And we already read that letter. Okay, now we start by the second part that we didn't finish it at the lectures. As you know, we have to finish the entire syllabus because this is most important, just because you cannot miss important concepts in the early beginning chapters. If you missed these concepts, you will not understand the advanced concepts in other chapters. So for the letter frequency analysis, we have another type of ciphers. Is called block ciphers. In block ciphers, we take a block of data and try to encrypt it. But here, there is no frequency attack. The attacker cannot use frequency analysis. Just for that simple displacement or transportation cipher, this is an example of block cipher. That transformation, transport cipher. The transport cipher here is using just the same letters of the original text. It is not going to use different letters, the same letters from the original text, but it will change the order of the letters, and that's the concept. If I keep, sorry for that sound, I cannot get rid of it because we have somebody's fixing our house, okay. For the transport cipher, as I said, we have a text, we change the order of the letters, only change it, not to shift the letter, no shift. This way, the attack, the letter frequency attack will not work with us in this attack. Okay. For example, let me explain it with an example. It's better. Uh, so, for example, if I have letters here like the pirate attack, I want to encrypt these letters with transport cipher, transport cipher. If I want to do the apply transport cipher to the pirate attack, what will happen? We can use block size. We use block size. This block size, okay, is is defined by letter. I think it is defined by letter N. N here is 4. Okay, so I divide the entire list of letters by 4. So I take the first 4 here, pi, R, A, and then T, E, A, T, and then T, A, C, K. I divided the text into four, 3 blocks of 4 letters because we have block size which is n equal 4. Now we have the transport function. The transport function is like that: sigma of 1 equal 3, sigma of 2 equal 1, sigma of 3 equal 4, and sigma of 4 equal 2. This is the key. If we can draw key here, this is our key. If somebody knows this key, he can decrypt our text. So how can we apply sigma of 1 equal 3? This means the letter at location 1 is moved to location 3. So P, which is at, we write down them here, pirate, A-T-T-A-C-K. Okay, and here the letter at location 1 is moved to 3, so this will be here. Location 1 is moved to location 3. Location 2 is moved to location 1. 2 is moved to 1. And 3 is moved to 4. 3 is moved to 4. And 4 is moved to 2. Okay? This is an application for the first block. Okay? For the second block, we apply the same thing. So we apply 1 is moving to 3, and 2 is moving to 1, and 3 is moving to 4, 3 is moving to 4, and 4 is moving to 2. And the last one, the same thing. 1 is moving to 3, 2 is moving to 1, 2 is moving to 1, 3 is moving to 4, and 4 is moving to 2. And this is the encrypted text. This is the encrypted text. Okay, the functionality here is important because if you see, we have an attack in Caesar cipher called letter frequency analysis. Letter frequency analysis. The letter frequency analysis will not work here. Why? Because we are using the same letters. We didn't change the letters. We just used the same letters here. So no change in the letters. So letter frequency analysis will lead to the same natural English, natural, I mean, not the plain text frequency analysis will lead to the same letters. So the attack will not succeed. I mean, for example, in plain text, we have E. E is the most repeated letter, and also in the cipher text, we will have E is the most repeated text. Why? Because we just changed the order of the letters. We didn't shift them. So letters are frequency are kept the same for the plain text and for the cipher text. Okay, so I think we can move here to the next slides. Okay, for the next slide, let me share it with you. And here, for stream ciphers, we have stream and block ciphers. Stream cipher, we have a stream of bits, and the functionality is applied on that stream. But for block cipher, we have a block and we apply the functionality on separate block. You can say stream cipher apply bit by bit or byte by byte, but the block cipher, we have to take a block of bigger size, and we apply the same functionality on that block size. As we said, as we saw, as we have seen in the transport cipher. This was a block cipher. So stream ciphers encrypt a bit individually, usually small and fast, common in embedded devices. We can use it in, for example, there is an algorithm A51. This is used in GSM phones. For block ciphers, we always encrypt a full block, several bits, and it is common for internet applications. Here we have a secret data. We apply, this is an XOR functionality. We apply this XOR using the secret key. This is SI is a secret key, and this is the XI is the plain text. We apply that. Okay, let me share. Okay, and we apply that. We apply secure key to the plain text to get YI. YI is the secure data. Secure data is transferred into the insecure channel and moved to the recipient. The recipient will do the opposite. The opposite in XOR is simple. It is the same XOR. I will show you in a minute why XOR is the same in encryption and decryption. The same functionality will lead to the plain text. Okay, so this is how to use encryption and decryption with stream ciphers. If you look at the functionality of this XOR, it is simple. It is XI plus SI mod 2. XI plus SI mod 2. And the decryption is YI plus SI mod 2. This is XOR. Okay, let me open up my screen and try to explain this for you. Okay, what is exactly XOR? For example, I have XOR functionalities like we have X, A, and B, and then we have 0, 0, and this is 0. We have 1, 0 equal 1. We have 0, 1 equal 1, and we have 1, 1 equal 0. So this is XOR, and the XOR functionality is defined by, you can, if you studied discrete structures, you will see it is like that. A and B, they are mutual. This means they don't have something in common, either you are in A or in B, not in both of them. Not in both of them, there is no intersection between A and B. So this is mainly XOR concept or logic, okay? The XOR, we can achieve the same functionality with this equation, exactly the same functionality. You can say Xi plus Si mod 2. Okay, so what about XA plus B mod 2? Okay, A plus B mod 2 means 0, 0 mod 2. 0, 0 mod 2 lead to 0. 0, 1 mod 2 will lead to 1 because 1 is less than 2. 1 plus 0 mod 2 will also lead to 1. And 1 plus 1 equal 2. 2 mod 2 will lead to 0. 2 mod 2. There is no remainder when we divide 2 by 2. There is no remainder. So the remainder is 0. And the mod is concentrating on the remainder. So take care of this. We can say XOR exactly. XOR A XOR B exactly. So A XOR B is exactly Xi or A plus B mod 2. Here, this example has A and B. So A plus B mod 2, the same functionality is applied. So why? This is why you can see in the slides the Xi plus Si mod 2 or AB or A plus B mod 2. Can we take an example? I will show you how the sender and receiver, we have insecure channel here, insecure channel. We want to send a stream of bits and we apply the XOR here between the original text, which is XI, and apply a key, which is SI, by using the XOR functionality. And at the receiver side or the recipient, we apply the same thing. We apply, or XOR is applied at the recipient side. We apply SI to get XI again. We have YI here and YI here. Okay, let's take this an example. For example, if I have the key or the plain text we have here, we have okay, plain text is 00110101. Let's apply it by example. And the SI is here equal 111000011. Okay, let's apply the XOR between these two. So we can say the result is here. 1 XOR 0 is 1. 1 XOR 0 is 1. 1 XOR 1 is 0. 0 XOR 1 is 1. 0 XOR. So we have finished. Okay, let's mark them. Okay, and this finished. This is also finished. This is 0, and this is 1, and this one is 0 with 0 is 0. This is 0 with 1 is 1. 1 with 0 is 1, and 1 with 1 is 0. So we have this 1, 1, 0, 1, 0, 1, 1, 0. This is the ciphertext. The ciphertext will go to the other side, reach to the recipient, and we will use the same key. This is private key cryptography or symmetric. Symmetric means we use the same key and at the server and the sender and the receiver. We use the same key. This key is sent to the other, the recipient, and the recipient apply XOR to extract the original text. If you see, this is 111000111. So we apply XOR again. 1 XOR 1 is 0, 1 XOR 1 is 0, 1 XOR 0 is 1, 0 XOR 1 is 1, 0 XOR 0 is 0, 0 XOR 1 is 1, 1 XOR 1 is 0, and then 1 XOR 0 is 1. Oh, this is exactly the same. This is exactly the same plain text. 101 01100. This is really, really good result. This is really astonishing result. It is really strange. We use the same functionality in encryption and decryption. The same algorithm is used in the encryption and decryption. And this is the magic behind XOR. This is the magic, really. Most of the encryption concepts that we will introduce in the next lectures will depend entirely on understanding the XOR. So this slide is very important. This lecture is very important just because of this. Everything we will introduce will lead to using XOR. Okay. Okay, let me open up my screen. Let me open my slides. Okay, let's get them back. So we know that xi plus si mod 2 is exactly XOR at the sender and the receiver. There are two types of synchronous or steam ciphers. We have synchronous and asynchronous. Synchronous means the key stream depends only on the key itself. But for asynchronous, maybe we can use the output of the XOR operation to make or to update the key. This is asynchronous. And this example we have used in our slides. We have used in our I displayed it with my handwriting. This is 0 XOR 0 equals 0, 1 XOR 1 equals 0, 1 XOR 0 equal 1, 0 XOR 1 equal 1. And this is the plain text, the secret text, and this is the cipher text. We apply the same thing here. The same operation is applied at the recipient. So cipher text XOR secret text will lead to the plain text again. Actually, if you look at the symmetric encryption algorithms, maybe you will not find Caesar cipher or transportation cipher. For that one, Caesar cipher for private key, and also transportation cipher for private key or symmetric key. You will not find them in the market, not commercially available. But there are different algorithms available in the market, and they are used by enterprises for securing their data. Of course, Caesar cipher and transportation is used only for understanding the main concepts behind encryption algorithms. Understanding them is very important, just because to be able to understand the complex algorithms in the upcoming lectures. For example, we have available AES. We will study it in chapter 4 or 5, I think. For this data encryption standard, also we will study it. EDIA is International Data Encryption Algorithm. Blowfish and RC4, RC5, RC6. EDIA and Blowfish, this RC5 and RC6 are block ciphers. They are block ciphers. So they take block of data and encrypt them. But for RC4 is a stream cipher. Okay, we finished now by symmetric key encryption. Now we move to another different way, as we can return back to this is an important slide. Okay. I just want to remind you by this slide. So for symmetric encryption, we used Caesar cipher, also transport cipher, uh, EDIA, this AES. These are types of symmetric key encryption. Here for asymmetric, this type of encryption is fast and is using the same private key in encryption and decryption. And it also has the problem of sending the key because the attacker may be able to capture the key. For asymmetric encryption, in this lecture, we will study only RSA. RSA will be explored as an example of asymmetric encryption. In asymmetric encryption, we have Bob want to send something to Alice, so he contacted her and asks her for her public key. The lock is public key. He's going to take this public key and encrypt data using his public, the Alice's public key. Then send the box to Alice, and then Alice will be open to open the box using her private key. So no keys are sent between sender and receiver. And this is also the magic behind RSA, just to not to send keys, just to send public keys like locks. Locks, if somebody captured the lock, it is not important to capture the lock, will not lead to any secure data. And only Alice with her private key can open the box or decrypt the data, nobody else. Maybe the hacker can capture the secure data, but he will not be able to decrypt it. Alice only will be able to decrypt it because she is the only one has the key of that encryption. And because RSA is important and used in cryptography as public key cryptography or asymmetric, public key and asymmetric, they are the same name. The RSA came from the names of the inventors of this algorithm. The names started with R, A, and L. I'm sorry, this is the first name, R, S, A. R, Revisit, Shammer, and Adelman. They are the three inventors or scientists that have been developed this algorithm. It is named after them for just to keep the inventors for the RSA, just to make them to relate this algorithm to them. And we always do this. We always do the same for new algorithm. If somebody invented new encryption algorithm, it is named by his name. The algorithm is named by his name. For example, El Gamal. El Gamal is a name for Arabic guy who invented El Gamal algorithm. Okay, so this is for RSA algorithm. The RSA algorithm use an encryption key with N and E, and N equal PQ, and P and Q are large primes, I will tell you all the details right now. Maybe say 200 digits. The primes must be very large, and E should be relatively prime to P minus 1, Q minus 1. E should be relatively prime to P minus 1, Q minus 1. Okay, let's move to an example. This is the algorithm. Uh, do remember that Alice and Bob want to send something to Alice. So Alice will do here K generation. So she is going to select P and Q, should be large primes. Prime means number is prime, you know, prime numbers. The number is divisible by himself and one only, not divisible by any other number. For example, 7. 7 is a prime number because we cannot divide it by 6. It is not divisible by 6, not divisible by 5, not divisible by 4, not divisible by 3, not divisible by 2. This is prime number. 11 is a prime number, but 12 is not a prime number because it is divisible by 3, divisible by 4, and divisible by 6. 20 is not a prime number. 21, no, because it is divisible by 3 and 7. These are examples of prime numbers. Prime numbers, we select two prime numbers, P and Q, and P and Q should be large prime numbers, just to make it difficult for the attackers to guess the prime numbers. Then the procedures go like that. We calculate n number, which is P multiplied by Q, and totient number. This is called totient number. Totient number is the factors of each prime numbers. The factors means the numbers underneath that prime number. Just understand it like that, and then we will introduce it in more detail in the future chapters. But anyway, this is quotient. The quotient, or totient, not quotient, totient by T, not by Q. So totient here is simply taking P minus 1 multiplied by Q minus 1. Okay, and then select an integer E. This integer, we select that integer to get a greatest common divisor between the totient and the E to be 1. So totient and E, they are co-prime. Co-prime, okay? They have a greatest common divisor of 1. If 1 means that they are co-prime. And then calculate D. D equal E minus 1 mod phi of n. Okay, I will let you know by example right now. Public key is E. This is a public key. You send it to Bob. Alice will send E and N to Bob. So he's going to encrypt his data using E and N. And then here private key is D and N. We created E and D, as you can see. E is a public key, D is a private key. So Alice will send E to Bob, and then when Bob prepare his data and send it back to Alice, she's going to decrypt it using the D, the private key D. And at encryption is done by Bob. He's going to encrypt his data using this equation, which is C equal M to the power E mod N. Then at Alice's public, she's going to use her key to decrypt the data, her secret key. So M equals C to the power D mod N, okay? And this is a numerical example. I will go by step for to understand the RSA algorithm, the mathematics behind it. I know this part is little difficult because we didn't introduce the number theory, but actually this is very basic concepts, not the entire concepts of number theory. I will introduce this example in more detail on my handwriting. I think it's better to use my handwriting to make you understand the concept more easily. Okay, so we can take the procedure, we follow the procedure of RSA. First step is to select two prime numbers. For example, we have two prime numbers, the smallest prime numbers ever, P equal 3 and Q equal 11. Okay, this is P and Q. We select two prime numbers. The first one is 3 and the second one is 11. They are prime numbers. They are not divisible. They are only divisible by themselves and 1. So 3 is not divisible by 2. And 11 is also not divisible by any number except itself and 1. So 11 is not divisible by 10, by 9, and by other numbers. So they are prime numbers. I select two prime numbers randomly, but they should be big prime numbers. For example, 200 digits, very long number. But for simplicity, we introduce the concept with very, very simple prime numbers. But this is not actually happening in commercial packages. The second step is to calculate n. N equal P multiplied by Q. N is multiplied by Q, 3 by 11 equal 33. This is n. Okay. This n, we use it to calculate the totient. I told you about the totient. 5n equal P minus 1 multiplied by Q minus 1. P minus 1, 3 minus 1, it means 2 multiplied by 11 minus 1. So it is 3 minus 1 multiplied by 11 minus 1. This means 2 multiplied by 10. This means 20. 20. Okay. So we have 20. Totient is 20. The calculations are simple, no problem. Now we go to the fourth step, which is calculate or choose a prime number E. Find the prime number E. Prime number should be prime number. We select that prime number to have a condition, which is must be coprime with 5n. Okay, so 5n must be not divisible by E. Coprime means, I will tell you right now that why they are coprime. 5n is 20. So, for example, if we select, for example, 4, 4 is not working. Because if 4 divides 20, I will select E as 4, but it is not working. Why? Because 4 divides 20. I don't want a number to divide 20 because they are coprime. Coprime means no one of them divide the other. So 4 is not working. 5 is not working. 5, because 5 divides 20. Okay. What about 6? We can select 6. We can select 7. But 6 is not a prime number, so it's not working. And also 4 is not a prime number, so it is not working. 5 is not working just because it divides 20, so it's also not working. So 6 is not a prime number, 4 is not a prime number. 5 is a prime number, but it's not okay because it divides 20. 7 is good choice, and 11 is also good choice. 13 is a good choice, 17 is a good choice, and so on. Until we get 19, we cannot get number more than 20. So E should be less than 5n. Okay? So we select the simplest one because to simplify calculations. So we have now the E. E equals 7. Okay? E equals 7. Okay. So we have N equal 33 and E equals 7 becomes, this is public key. Public key Now, Alice can send this public key to Bob to encrypt his data using this public key. But when the data return back to Alice, she will not be able to decrypt it because she didn't create the private key yet. So the next step is to create the private key. This is a public key is okay now, but we have to create a private key. How to create a private key? The private key should be created so that E multiplied by D equal 1 mod 5n. This is the condition. This means the, the multiplicative inverse of E. D should be multiplicative inverse of E. You know, if we have X equal something, if we want the multiplicative inverse of X, so we divide X by X. We divide two sides by X. So we say X by X equals something by X. This means 1 equals something, okay? So here we have X minus 1 multiplied by X equal something by X. This means this is the multiplicative inverse of X. This is the multiplicative inverse of X, okay? Because they are equal 1. Now I multiplied two numbers and we have 1 mod 5n means we have a remainder of 1 mod 5n. This means these two numbers are multiplicative inverse. Why we select them multiplicative inverse? To be able to use the same key here, that key here, we use it in decryption. To make opposite way. Inverse means opposite. So encryption go this way and decryption go to the opposite. To make it able to go to the opposite direction and for example, this is X and this is Y. I want to get X from Y. I can do that. I can do that if the function is reversible or we have an inverse. It can be inversed. It has an inverse. If it has an inverse, it is able, we are able to create or get the plain text out of the ciphertext. So this should be a multiplicative inverse. What is the number to multiply by 7 will lead to 1 mod 20. What is the number to multiply by 7 lead to 1 mod 20? Okay, let me try. If it is 1 by 7, 1 by 7, it's far away from 20. So the remainder will be 13. So it's far. So 1 is not working. What about 2? 2 multiplied by 7 is 14. 14, we have a difference of 6. This is not going to work. What about 3? 3 multiplied by 7 is 21. 21. And this is very perfect because we need to have 21 is 20 and we have a remainder of 1. 20 result and a remainder of 1. And this is perfect. Sorry, this is perfect. So 3 here is working because if I multiply 3 by 7, it will give me 21, which has a remainder of 1, mod 20. It has a remainder of 1, mod 20, okay? So I multiply 3 by 7, it has a remainder of 1, mod 20. Because the result is 21, okay? So now I succeeded to get D, and D equal 3. This is, we have N equal 33, N equal 33, and D equal 3. Now I have my private key. So Alice can keep this private key to use it to decrypt the data. This is the entire procedure of RSA in a simple, very simple way. I know there are some calculations here, but if you follow up, this is very straightforward. You can understand it. Okay. And now I will take an example to show you how to use the private and public keys of Alice and Bob to make encryption and decryption. Okay, let's see an example, working example. Uh, for example, we have Alice. I will show you this is Alice. She has her private key, which is 33 and 3. This is her private key. And Bob has public key, which is 33 by 7. And we can use, Bob can use the public key here. So at the beginning, Alice sent the public key to Bob. Bob will take the data and encrypt it using his public key, using this one, C equal M to the power 7. This is the public key, mod 33. So we have here the encrypted data, something not ordered. This encrypted data is sent back to Alice. This is the encrypted data. Nobody can understand what is inside, but so we apply the opposite way around. So we apply it like that to get the data back. So we applied the private key here, M equals C to the power 3 mod 33. Okay, to get the plain text back. Now there is no keys are sent. Only public key is sent between Alice and Bob. And Bob can take this public key and encrypt the data using this public key. If somebody take this, he should know the private key was 3. Nobody knows that 3. He can try many different types of prime numbers, but if the prime numbers are very big, he will not be able to get the keys. So Alice will take the encrypted data and apply this equation to get the plain text. Okay, that's for our example. And for 33, we need 33 letters. I have supposed A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. And also I want to add 26, there are 26 letters, so I should add some special letters like I, at, hash, dollar sign, and percentage, and the and the star. This is 1, 2, 3, 4, 5, 6, 7. 7 is added to 26, give us 33. Okay. Okay. These are the letters that we want to use it as our alphabets. We can say this is our alphabet. Let me pause for a second. So this is our letters, alphabets, and we will use it in our example to make encryption and decryption. Suppose that we have an example that we want using this alphabet, this expression, I love you. I want to encrypt this sentence. Now I have to get the indices of each one of them. Okay. Okay, let me see. 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, so it started with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. These are the alphabets and their index. Okay, we can get I with 9 and L with 12 and O with 15 and V with 22 and E E with 5 and Y with 25 and O with 15 and U with 21. U with 21. Now I have these numbers. I can apply the encryption. Okay, so I can say, okay, I can apply this one, C equal n to the 7 mod 33. So 9 Ci equal m, which is 9 to the power 7 mod 33. Okay, so if you use your calculator, this will lead to 15. And 12 to the power 7 mod 33, if you use your calculator, will be 12. Okay, and also for the other letters, which is, okay, 15 to the power 7 mod 33, which will lead to 27, and 22 to the power 7 mod 33. Okay, let me write them all. 5 7 mod 33, 25 7 mod 33, 15 7 mod 33, and last 21 mod 7 to the power 7 mod 33. This will lead us to 22 to the power 7 mod 33. It will be 22. This is equal to 5 to 7, 14, 31, 27, 21. Okay, these numbers I will use the opposite way around to decrypt the data, to take the secure data. Just to go to the opposite way around. Here we have 15, so we go to 15 and see O. 15 is O, then 12 is L, and 27 is I, or that sign, and then V. If you continue this way, 22 will be V. Yes, V. If you continue counting, this will lead to this secret word, like that. This is the encrypted text. I can send this encrypted text to Alice, OLIVN, like that, to Alice, and she's going to use the opposite way. She's going to use these indices. She's going to get all the indices of these letters. Okay, so This O is located at 15, 12, I is at 27, V is located at 22, N is located at 31. No, it is not. N is located at 14, 31, 27, 21. She's going to get this and apply the other, that one. So she's going to get something like 15 to the power 3 mod 33 equal what? And also 12 to the power 3 mod 33 and 27 to the power 3 mod 33 and 22 to the power 3 mod 33 and 14 to the power 3 mod 33. Okay, and 31 to the power 3 mod 33 and 27 to the power 3 mod 33 and finally 21 to the power 3 mod 33. If you calculate it using your calculator, this will lead to 9, and this is 12, and this is 15, and this is 22, and this is 5, and this is 25, and this is 15, and this is 21. This will return the same sequence of letters back, because if you look at 9, 9 is I, so I, and 12 is L, I, love, O, V, E, Y, O, U. This will lead to the same plain text again. Okay, that's all for RSA, and this is an example of how to use it in a practical way. No sending of the keys. The keys are kept at Alice's side, and it's more secure than other approaches. Compared to other approaches, it's more secure. But as you see, this contains many calculations. As you see all these steps here, these calculations are important to use RSA algorithm. Okay, and we get all the data back using the private key of Alice's, using the equation or the 3, which was the private key for Alice, and 7, which was the public key that Bob used to encrypt his data. That's all for today. Thank you very much for listening to me and watching this lecture. See you in a good health. Take care of yourself, and goodbye. Assalamu alaikum.